Hello everyone, in this video we're going to cover section 4.1 on direct proofs and counterexamples. So let's check some key definitions. So first, in mathematics we must define terms very carefully and very precise because proof rely on manipulating definitions. And so if you have ambiguous definitions, you might end up doing invalid proofs. So you need precise definition to prevent misunderstandings. And mathematical communication is going to rely on those exact meanings. The key principle when proving something is that you must use the formal definition and not your intuitive understanding, not examples. Okay? Let's check. For example, if you define an even integer, we can say an integer n is even and only if n is equals twice some other integer. And similarly, we can say an integer is odd if and only if n is equals twice some integer plus 1. Symbolically, this can be represented like this. So we can say n is even if and only if it is k that belongs to the integer such that n is equals to k, and n is odd if it is this k that belongs to the integer such that n is to k plus 1. Now notice that the variable k can be any integer, and we can have some examples here of even numbers. We can have -4, -2, 0, 2, 4, 6. Odd numbers, we have -3, -1, 1, 3, 5, 7, 9, so on. Every integer is going to be even or odd, but never is going to be both. So it's going to be in one camp or the other. Notice that 0 is even. We can see that 0 is even because we can represent 0 as twice some k. What k do you ask? Well, we can give 0 as the k. So we can represent 0 as twice times 0. And that will mean that we found an integer that works for the relationship of even, and 0 is defined as even. Now, -1 is an odd number. Notice that to prove that it's odd, we need a k so that -1 can be represented as 2k plus 1. Well, if we set up k being -1, then we're going to get 2 times -1 plus 1, which will be -2 plus 1 or -1. So indeed, we found that integer that make it work, and we're going to have that -1 is odd. Now, we can extrapolate this to more complicated things. So we can say if x is an integer, it's going to be 6x squared plus 8x plus 3 odd. And yes, we just need to find a way to make this into the definition of odd. So for example, I'm going to factor out, I'm going to write 6x squared plus 8x plus 3. And this plus 3, I'm going to write it as 2 plus 1. And then I'm going to factor 2. So I'm going to represent this as 2 times 3x squared plus 4x plus 1 plus 1 more. So in this way, since 3x squared plus 4x plus 1 is going to be an integer, given that x is an integer, then this is the 6x squared plus 8x plus 3 ends up being from the form 2k plus 1, where k is an integer. And so by definition, this expression is going to be odd. Now, we can have a definition for different things. So for example, we also have prime and composite numbers. An integer is prime if it's only divisible by itself and by 1. So you can kind of see it as if the number n bigger than 1 is prime, only if, given that n is the multiplication of two numbers r or s, then r or s gotta be equals to n. And therefore, the other number is gonna be 1. So this means it's only divisible by itself and by 1. Now, in terms of composite, an integer is composite if you can see the number as the multiplication of two other numbers that are smaller than the number that we're trying to get. So notice I write n is equals r times s, and r is a number between 1 and s is also a number between 1 and n. And the multiplication of those will give me the n number. In simple terms, we can say that a composite number can be factored into integers both greater than 1 and less than n. Now, it's important to remember that 1 is neither a prime or is a composite. There's none of this. Now, by definition, prime numbers must be greater than 1. And so it doesn't work that way. 1 is not bigger than 1, so 1 will not be prime. The first actually A prime numbers will be 2, 3, 5, 7, 11, 13, 17, and 19. If you check any of those, they're only divisible by itself and by 1. Talking about the first prime numbers, we can also do the first 8 composite numbers, which is 4, 6, 8, 9, 10, 12, 14, and 15. Some of those are divisible by 2. Some of those are also divisible by 3. And so they're divisible by numbers different from itself and 1. And so that's why they're composite. Now, let's talk about direct proof, which is the important meat of this section. So, first than anything, we need the definition of what is a theorem. So, a theorem is going to be in a statement that is known to be true because it has been proven. Okay? There are certain related terms to a theorem which work in the same dimension. For example, a lemma is a theorem whose main purpose is to help prove another theorem. So it's like an intermediate result to get to the result of the theorem. A corollary is a theorem that follows quickly from another theorem. It's like an immediate consequence of that theorem. A proposition is going to be a less important theorem on the whole scale of the proofs and the results that we're trying to do. All this are going to require rigorous proof. We're going to need to prove very carefully each of them. So the most important thing that you're going to have in this proof structure that we're going to be doing in the upcoming weeks is going to be the 5-step structure. First and anything, we want to prove statements of the shape for all x that belongs to a domain. If p of x, then q of x. We're pretty much doing an implication. You're working in implications. So the first step of the 5-step structure is going to be you need to state the assumptions. So for example, you're going to say, suppose that x belongs to the domain and p of x is true. So that's going to be my assumptions. Then what you need to do after is you need to formally define the assumptions. You need to write that p of x using the formal definition. You need to write what p of x means. Then from that, you're going to use algebra, logic, or previously stated theorems to manipulate that definition into what you want to get towards the conclusion. Then you're going to arrive at the definition of the conclusion, and you're going to show that the formal definition of Q is satisfied. Then you're going to state the conclusion that hence that Q of X is going to be true. This way of working the proof shows that if the hypothesis is true, then the conclusion is going to follow logically. Okay, but let's show how this works so you can actually do it yourself. So let's prove a theorem. The first theorem is the sum of any two odd integer is even. So to prove it, we'll first start with the assumption. We suppose that m and n are odd integers. We pick two numbers and we assume that they're odd integers. So now we're going to use the definition of the assumption. So by the definition of odd, we say that it says integers r and s, so they can represent m as 2r plus 1 and 2s plus 1. Notice that I'm using different letters. We need to always use different letters because they're different numbers. Now, from here, we're going to go to the phase of manipulation. Because we're trying to prove that the sum is even, then we're going to do the sum. So we do m plus n, and then m plus n is 2r plus 1 plus 2s plus 1. Now we add those things together and we get 2r plus 2s plus 2. We can now factor that 2, and we're going to get that this is twice r plus s plus 1. But this r plus s plus 1 is going to be an integer. Why? Because r is an integer, s is an integer, 1 is an integer. So this entire thing is an integer. And then we can see it as m plus n is 2k. That is going to be the definition of the conclusion. We're saying now the sum is an even integer. Okay? Finally, we state the conclusion. We say, hence, the sum of any two odd integers is going to be even. Notice sometimes we use the symbol, which means querendus, erendus, demonstrandus. Sometimes it's in black, and this marks the end of a proof. Now, let's do another one so you can further the idea. We're going to have the sum of two even integers is even as well. Well, this is the same way. We go about it the same way. M and N are going to be even integers. We check the definition of the assumption, and this means that it's going to say integers R and S, so that M is 2R and N is 2S. Then from manipulating, I do the sum. M plus N is going to be 2R plus 2S, which can be factored as 2 times R plus S, which really, if we make K being R plus S, but notice that K is going to be an integer since R and S are an integer, and therefore M plus N is going to be from the shape 2K. So by definition of even, M plus N is going to be even. Now, let's talk about proof and existential statements. If an existential statement is something of the shape exists in X that belongs to D such that P of X. The method here is going to be finding a specific value on the domain for which P of X is true. So this is much more relaxed. This is much more relaxed because we only need to show an example. Existential statements only require that you show a brief example. So the structure of the proof is going to be, you state the value of X that you're proposing, you verify that belongs to the domain, and then you show that P of X is true for that particular value. Now, one example is enough to prove an existential statement, and this is very different from a universal statement where one example proves nothing. Be very careful when you're doing proofs. You want to make the difference between those two. Now, let's give an example here. So there exists integers m and n, so that m is bigger than 1, n bigger than 1, such that 1 over m plus 1 over n is an integer. Well, I can just take m equals 2 and n equals 2. Notice that they verify that they're both bigger than 1. 2 is bigger than 1, so we verify that. And then we calculate 1 over m plus 1 over n, which is going to be 1 half plus 1 half, and then you're going to get that this is 1. So the sum is an integer. And so we have that those integers exist. We're done with our proof. Now let's talk about common mistakes. So the first thing is that you're proving by example. In particular, when you're doing universal statements, testing is not going to be a proof of something that says all even integers do this. The right way to do it is to use the definition and show that it works for all even integers. You gotta be careful also with not using the formal definition. For example, if I say n is even, so it's divisible by 2, this is not good. We need to write mathematically. We say if n is even, then exists a k that belongs to C, such that n is equals to k. Now, another mistake is assuming what you need to prove, which is, let's say, suppose that m plus n is even, then m plus m is equals to k. If you start with the hypothesis, you cannot start with the conclusion. So you gotta be careful with that. If I want to prove that the sum of two integers is even, I gotta state first that each of them is even and show that the whole thing is even at the end, not just jump into the final conclusion. You gotta be also careful when you're using different numbers that you don't use the same variable. So for example, if we're using m is to k and n is to k, that will mean that they're the same number because m is equals n. Being both of them 2k will imply that. The right way to do it about it for different numbers is you gotta use different letters. So m is gonna be to r, n is gonna be to s, different letters for different numbers. Now, you also gotta be careful not checking integer requirements. When you write that n is equals to k, you must verify that k is an integer, or otherwise you can just get different things. K can be a real number, and that will give you different things. So you just gotta be careful with that. And let's not confuse definition. N equals 2k is even. N equals odd is 2k plus 1. So you gotta be careful not to mix them. Now, in summary, for any proof that we're going to make, definitions are going to be crucial. You want to take into account that even is n is equals 2k, that odd is equals n 2k plus 1. Prime numbers are numbers bigger than 1 with divisors only 1 and n. The direct proof structure, the 5 steps, is you state your assumptions, you do the definition of the assumptions, you define formally, you manipulate, you reach to the conclusion definition, and you state the conclusion. You gotta follow those steps for everything that you're doing. Finally, existential statement only are proved by finding one example, and you verify that all conditions are met. Okay, so let's take a look at more of this on the examples for the section.